very much for inviting me. It's very exciting always to talk about these things to people who are coming in and interested about the new developments on what people can do with X-ray electron lasers. So yeah, my title is about single particle imaging at XFELs and the birth of 0 femtosecond crystallography. And first, I would just like to start with the acknowledgements. And there's a lot of people involved in these projects, and I decided there's no space for all the names, so I just put institutions, and the ones that are most involved are on top, and then you can see there's a wide variety of institutions. So it's a pretty large project, and this involves both the single particle and the nanocrystallography. And as a starter, so I imagine you're familiar with crystal diffraction. So if you don't have a crystal, but you only have a single particle, like say a duck, and then you just get your diffraction pattern, you'll get some kind of continuous diffraction pattern of a single duck, which looks kind of like this. And then if you take the Fourier transform of this, you get the autocorrelation of the duck, which looks like kind of this halo around the duck here. So this gives you some information about the duck, and if you're clever about it, you can actually use this information, so from this diffraction pattern, to obtain back the structure of the duck. And I'll talk a little bit more later about it. So why are we interested on single particle imaging, and why are we even talking about this? Because the thing that enabled people to start to think about this and to actually make experiments with this is the arrival of these free electron lasers, which have an amazing increase in peak brightness compared to previous X-ray sources. So they're about 1 billion times brighter in terms of the peak brightness compared to synchrotrons, third generation synchrotrons. So it's been an amazing increase, and there's all kinds of new experiments that one can do with such a high flux. And one that had already been proposed quite some years ago is this idea of the diffraction before destruction. So one of the issues when you always try to look at things at high resolution is that whatever you use to look at things will damage your sample, and it will cause radiation damage, and then you're no longer looking at the thing that you started with, but you're looking at some damaged things. So if you have some light which is, or if your probe is sufficiently short, we're talking here in femtoseconds, then you can actually probe your sample faster than the damage develops, and you will get an image of the undamaged sample, or very little damage, so damage didn't have time to fully develop. While if you have a long pulse, say hundreds of femtoseconds, or if you're talking can be much longer, I mean, you start to get just mostly the picture of the completely destroyed protein. It would be a protein. So here is just a quick animation of the dream experiment that we'd like to do. So you have this XFEL shooting down the beam path, and then you inject your particles into the path of the X-ray beam, and the X-ray beam intersects the particles and diffracts the light, and then you get a bunch of diffraction patterns, and you don't know the orientation of the sample, but you hope the sample is always similar to each other, and then you try to classify the patterns that you get to try to average them and increase the signal to noise. So this is very similar to what you do in cryo-EM, for example. And after you have averaged them to improve signal to noise, you just look how they fit with each other, the different patterns, because you know they all belong to the same 3D Fourier space. And after you have the entire 3D Fourier volume sampled, you can actually phase the diffraction pattern and recover the sample that you're interested in. So this is ideally, so this is an animation from LCLS that I took, and that's the machine in Stanford where the free electron laser, the first hard X-ray free electron laser. That's the idea. So we still have some way to go to get there, and I'll just start a bit from the beginning, where we first started our experiments in Hamburg at the facility which is nowadays called Flash. This was the first very soft X-ray free electron laser. This was in 2006, and the wavelength was 32 nanometers, so this is much longer than what you're used to. But it had 10 to the 13 photons per pulse, and a couple of femtoseconds the pulse is long, and it actually provides lots of pulses. And at this point, there were many people that were very skeptical about this idea of the diffraction before destruction because they didn't really think that it would work. And so this was the first demonstration of this principle. So we only had silicon nitride membrane with some things etched, and then we just shot the FEL at it, and then we collected the diffraction using this mirror onto the detector, like here, and then the straight beam just goes straight through the hole in the detector. And this worked really well. It worked so well that it was actually the time when the facility changed its name to Flash, because they thought that this was like a flash imaging, and they changed it to Flash because they were called the vacuum ultraviolet electron laser, which people didn't like the names. Flash. So this is the diffraction pattern. This is the SEM image. This is the reconstruction using the diffraction data. We have a good agreement. You can even see like some small specks of dust in your sample, and so on. So it works very well. You take a second shot, and you see nothing. I mean, because the first shot makes a huge hole in the membrane, so there's nothing left to look at with the second shot. So this worked spectacularly. So how do you actually do the reconstruction from that diffraction pattern into the object that you're interested in? And this is simpler than it sounds, because you use only two constraints when you do the reconstruction, or the phasing. And the first one is what you also use in nanocrystallography, is that you have some kind of intensities, and you have to make sure that your object matches those intensities. So the Fourier transform of your object matches the intensities that you measure. So that's simple enough. The other constraint, which we have here, which we don't usually have in crystallography, is we have a so-called real space constraint that your object is isolated. So for these things to work out, you have to have your object and then either nothing around it or something which is very constant around it. And you have to have an idea of the extent of your object. And there are algorithms that try to get this automatically or throughout the reconstruction. But let's say that you know that so we're going to talk about the place where the object can be. We call this the support, and then your existing estimate of the object is in this blue, in this dark blue. So here on top we have the support is some kind of weird shape, and then your initial estimate of your object is this dark blue part, and your final estimate is just the intersection of the two. And so that's what you call fulfilling the support projection. So these are the two kinds of projections. So fulfilling the intensity, so you just scale your amplitudes so that they match the intensity that was measured experimentally, and the support projection. And then you do this over and over again. So you start with some object, you take the Fourier transform, you get some pattern that it should come from this object. You apply the Fourier space constraint, and then you back Fourier transform, you get a new object, and then you apply the real space constraint. And now, almost for sure, your object will no longer fulfill the Fourier space constraint again, so you will iterate and iterate. And at the solution, they should fulfill both constraints and nothing should move. And this is all, this is kind of simple. There are some issues with it, so this can be viewed as projections onto sets. So you have the set of all points that fulfill the support constraint, and the set of all points that fulfill the amplitude constraint. So these are like all different structures that could fulfill one or the other. And then you just project onto one and the other, and so on. The issue being that this set is not a convex set, so you can get local minimas and you can get stuck. And there are all kinds of algorithms to try to help you out of these situations. And I will not talk about it now, but the idea is simple. You just apply those constraints alternating, and hopefully we'll get to a solution. And this is just an example. And you can see gradually you start to see the image appearing as the iterations progress, and in the end you pretty much get a stable image. Okay, so this is all with the made samples, so nothing really biological. It was all manufactured. So now we actually started to do our first experiments with some relation to biology. So This was in the end of 2006, and we used Picoplankton. This was our Picoplankton kindergarten growing in Hamburg. And because people didn't really think that the people who build these electron lasers are physicists, they're not biologists, so they didn't think that someone would require a biological lab. So we didn't have a lab. So what we did was, there was a container that actually had, that went to Antarctica to collect some samples and had kind of a lab inside. And we brought that container to Hamburg, and this was our container, lab container, which was where we prepared all our samples and characterized them and everything. And using the picoplankton grown there, we actually got the first diffraction pattern from a single cell with a single shot, and it diffracted nicely, and everyone was very happy about this. Yeah, this is experiment picture from the time. Yeah, and we actually also a bit later we managed to reconstruct this, and it worked fine except for being at very low resolution and the wavelength being so low, meaning that you actually don't penetrate through the cell, you get only a shadow image. So, but in principle, it works. Nitride membrane, and then they were kind of drying out in vacuum for a long time, so they were completely dead. We wanted to have something a little bit less dead, let's say. So and also for the, when you want to do this with proteins, you don't want to have the protein deposited on a silicon membrane and then shot at it, because you're going to have so much background from the membrane that you can't see anything. What you want to do is you want to have the isolated sample floating in vacuum, and then you hit them with the X-ray. And that's why we developed this aerosol injector. So the aerosol injector starts with small droplets of the sample you want, and then the sample dries as it goes through this lens stack, which is basically a series of holes which act to focus your sample into a particular spot, which hopefully is the spot where it intersects the X-ray laser. So you put your sample through this, and you should end up with a beam of particles. And then you try to intersect the beam of particles with your X-ray. And we got diffraction, and we managed to reconstruct this. And we got, again, some kind of image of a cell. Again, we're very happy that we actually managed to get things to work out, especially this part of the injection was kind of hard because you have to intersect two pretty small beams, but it all worked out. Again, the reconstruction doesn't really show anything in the interior because of the wavelength that we're at, very soft X-ray. So this is basically the outline, but it was basically preparation for the next step, trying to go to harder X-rays and having developed a bit of the techniques. So in 2009, finally, the LCLS arrived, the first kind of real X-ray for electron lasers. So we're not talking anymore on 32 or 16 nanometer wavelength, but we're talking on 1 nanometer in the beginning. And nowadays, hard X-rays also. And it was quite a spectacular arrival because it lased, the first light was in around April 2009, and 4 days later, it achieved saturation. So I didn't really explain how electron lasers work, but you have a very long undulator compared to a normal synchrotron, and with that long undulator, you can achieve actually a much higher amplification than what you get in a normal synchrotron. And they actually achieved the maximum saturation before they used all the undulators that they had built. So it worked even better than what they thought. And they got this very nice laser, very nice beam. And just a couple of months later, then we went there for the first experiments. And we started with cells, and now we're trying to go a bit smaller things. And we went for a virus, but because we were not very confident, we went for the biggest virus we could find. So the Mimivirus, that's pretty big. That's about 450 nanometers in diameter, pretty huge. And we eventually want to get something like this. So it's a long way there. So we had this amazing beam. We didn't have a chamber, and we didn't have a detector in the beginning, which was kind of a problem if you try to do experiments without the detector. you can't get much. So fortunately, the Max Planck Institute volunteered to provide a chamber and a detector, which was actually, this is the CAMP chamber that is provided by them. And the detector also, the PNCC, it's an amazing soft X-ray detector. It's actually still the best that we've used, even several years later. And with this setup, same kind of thing. So we have the particle injector from here, the X-ray beam from here. You try to intersect them, and you get the diffraction signal here. And this is just to try to hope that your detector doesn't get coated with the virus that you're injecting, and still did get coated. They were quite unhappy with us. But we got some reconstructions. This time a bit better than before. You actually get to penetrate through the virus. There is an issue though, which is the fact that you don't quite, there's problems with limited dynamic range of the detector, so you don't quite get the whole data, but you have kind of a hole in the middle, so you have low resolution data missing. And this causes, there are degrees of freedom in your data set that you can't really know for sure. So you have kind of a high resolution, the high resolution you know, the lower resolution you don't, so you can assume different models, and that's what we kind of had to do at this point, which is kind of a silly technical limitation of the detectors at the time. Also, at the same time was when the first nanocrystallography was developed, was done. So it was actually on this pretty much one ping-pong after the other, and so the nanocrystallography was, I don't know how much you're familiar with this, but there's also same liquid jet, so it's very similar to what we were using as the source for our aerosol. So this is exactly the same thing. It's called a gas dynamic neutron nozzle. So we have the jet going through here. There's a gas going around. The gas compresses the liquid jet. It goes at high speed and accelerates the liquid. The liquid gets thin, and then the LCLS intersects the liquid jet. And in this liquid jet, there's a bunch of crystals in all kinds of random orientations, and you get these very nice diffraction patterns. And you can even see, you can actually look at one of these on the back detector and see the shape transform of the crystals, so you can even get an idea of the size of the crystal and so on. And there are some crystals that are really small, so like on the order of 10 unit cells on the side. So after you have this data, the problem is how do you get your intensities back, because you don't know what are the angles. So you can kind of from the position of the peaks, you can index this, but there's the slight issue that the crystals are not all the same, and there's actually also some variation in wavelength, because the FEL, the way the light is created, there's some natural variation, and we didn't know exactly the wavelength. And of course the orientation, we don't know, because you don't know the orientation of the crystal, but also you don't rock the crystal, so you don't get an entire bracket, but you get only a partial bracket. So how do you get from there to full intensities? And there were two guys that were working on this, so it was Rick Kieran and Tom White, and they just tried, okay, let's just use the indexed values, and we just sum them all without caring for the fact that we don't know what is the wavelength and we don't know what is the exact partiality and so on, and just let's hope for the best. And it kind of worked out. So they did get some intensity that made sense, and using molecular replacement you can get the structure to quite decent resolution. And so nowadays this is used quite a lot, and there's been some improvements, but actually there's still kind of a gap in terms of R factor between the things, kind of intensities you get using this method and the conventional crystallography, which is not completely understood, but a lot of progress in this area. So this was around 2009 and at the end, and this was also a few months later I started to think about this CXIDB, because we're starting to get all this data from the LCLS, and we thought it would be great to have a place to put this, and also that other people can access it, because it's very hard to get time at 3-electron lasers. So if you have more people then trying to look at the data, you might be able to make progress a bit faster. And that's kind of how this was born. And we continued our single particle diffraction. So we started at these cells and then the minis. Now we went to carboxysomes, which are which are about 100 nanometers in size, so going lower and lower in terms of size. And this was the first time that we actually had data where we actually have no missing data, or we can interpolate perfectly the missing data that we have, and we could automate completely the reconstruction from these kinds of images, and get. So we're expecting to get some icosahedron shapes. This is the icosahedron model. They are very similar. We have thousands of images on the order of 50,000. We could actually reconstruct this automatically, all these 50,000 images, and we got the resolution on the order of 18 nanometers, which was more or less limited by the detector. So we're kind of happy with this. And it was the first time we can actually do this kind of things automated. But we're always trying to advance to smaller and smaller things because we want to get to these single molecules at some point. And so this was already in 2013. We started to get the first signal, measurable signal from smaller viruses, from more normal-sized virus. Here, for example, MS2. But you can see the signal is not very strong. You have basically the central bump and one ring, and you have a bunch of photons. It's not spectacular, but it's something. And there are predictions, or there have been papers showing that if you have, as long as your noise is low enough, which is a critical point, so you need to get detectors that are good enough and also low enough background on your beamline, such that you basically have very little parasitic scattering from mirrors and other things in your beamline. And if you manage that, then even with this kind of data, you could actually get pretty high resolution reconstructions, as long as, of course, you have to measure the rest of the data. But they managed to do reconstruction with a kind of signal on the order of 10 to the minus 3 photons per pixel, which is quite amazing, I think. And also in 2013, we got the first new structure coming from an XFEL, and this is Catepsin B, which was actually a structure from crystal grown inside of a cell, which was kind of cool. And science thought it was one of the 10 top breakthroughs in 2013. So everyone was very happy with this. And nanocrystallography has continued to develop, and now there's been experiments using pump probe on photosystem 2, for example, using these kind of laser on, laser off experiments to try to see the reactions. And people also do spectroscopy at the same time, and all kinds of cool experiments that people have been doing. And I haven't been lately so much involved with in nanocrystallography, but I think it's. I'm sure it will. In the beginning, there were lots of people who were kind of skeptical about these electron lasers. They were so expensive, and we don't really know what we're going to do with them. But I think now a lot of people want to use them. So there's a lot of demand, and I'm sure that I'm sure that the DOE sees that this has been quite a great success. And also like comparisons of data between Synchrotron and FEL, showing that you can get, which is, for me, it's kind of expected, that you can get better quality data at an FEL compared to the Synchrotron, especially if you have things which are fragile and you have radiation damage going on at the Synchrotron. So this is just a recent paper in Nature from Axel Bunger's group, where they looked at the same sample at an FEL and Synchrotron, and at Synchrotron only 1 out of 85 crystals diffracted to 4.1 angstrom resolution, and at FEL we got 61 out of 72 diffracting at the 3.5 angstrom resolution. So clear improvement between the two sources. Quite valuable, I think, for to have a source that can give you this kind of improvement. On the single particle imaging side, the SLAC realized so where LCLS is, they realize that this is something that they really want to get to, and it's hard to achieve this, to do this kind of experiments. And the way that things were being done at the time was that you submit a proposal, like for a normal beam time at Synchrotron, submit a proposal, and then you either get time or you don't get beam time. But there's kind of a lack of a strategical vision for this particular technique, especially for things that were kind of trivial or that were not really science, but things like characterizing your beam line and your detectors and so on. These didn't get any beam time, and this was a real bottleneck, a real issue for people trying to do very carefully experiments where the signal is very low. So the management of LCLS decided to set up this single particle imaging initiative with the goal of achieving 3 angstrom resolution on a single molecule. And there's a bunch of people here taking part on this initiative. And this has been working now for 1 year, and it's been working quite well. And we've achieved, we have very, very nice data, which hopefully should be published soon. In the meantime, we also got the first 3D structure from the single particle imaging, very low resolution, so it's 100 nanometer resolution, but it's kind of a proof of principle, just showing that what kind of things are possible. And most importantly, it was basically done just to develop the validation methods that give us confidence that the result is correct, and hopefully then the same kind of techniques will be applied to these large data sets that are being collected in this single particle imaging initiative. And we are confident that we already have actually reconstruction from this SPI. So this is 100 nanometer. We have already 50 nanometer resolution, so way, way better than this. It's just a question of using more data and actually measuring putting the detector in proper position and so on. But this was a great effort in terms of developing validation and software to be able to put everything together. So for the future, we have the European XFEL coming up at the end of next year, which will provide you about 300 times more shots than what you have per second than what you have at the LCLS, or not 300, but almost. So you have 26,000 shots per second at the European XFEL compared to 120 shots per second at the LCLS. And you're going to have an amazing amount of data. And it has this kind of funny structure. You have all your pulses come together, and then there's a lot of space without anything. And then there's, again, lots of pulses, which is going to make experiments hard, but it's going to be an amazing opportunity. And there's been recently an interesting development from the group XFEL, which we collaborate in Hamburg, which is kind of a convergence between this nanocrystallography and the single particle imaging. And this has to do with what I started with. So if you have a single duct diffraction, you get a single particle kind of diffraction pattern. If you have many of them in solution, they don't have a relative orientation with each other. You get some kind of Sachs patterns. So you lose all kinds of orientation information. But if you have them only with translation disorder, you still get your single particle diffraction pattern, assuming that you kind of ignore the interparticle interference, which is it's a safe assumption as long as you have enough particles there. And what they found was that if they looked at their their nanocrystallography diffraction patterns at the regions where there is no longer any bragg peak, if they were very careful and trying to orient different patterns, they actually saw some continuous diffraction data there, and they managed to improve the resolution of some of their maps by a significant amount. I think from some of them from 4 to 3 angstrom, using this kind of continuous diffraction pattern that they could see in between outside of the brackets. And this has been kind of really exciting, and I think that this kind of they will publish. This will come out soon, and I'm sure there'll be a lot more people interested in doing these kind of things, because if it really, they're going to do some experiments now and see if they can reproduce this in other kinds of proteins. But if this really happens, it's really exciting. And that's pretty much it. I left some time for questions. Thank you very much.